What if a $300 setup could store enough heat to keep your home warm for days with zero power bills? They tell you survival in winter comes with a price tag: gas connections, expensive heat pumps, or massive solar systems that cost more than most people can afford. But that belief starts to fall apart when you look at what's quietly happening in remote, cold regions of the world. In places where winter isn't just uncomfortable but brutal, people are finding ways to stay warm without relying on monthly bills or fragile systems. This story begins in a rural landscape where temperatures drop far below freezing, and snowstorms are not an exception, they are routine. In that environment, one simple decision changed everything. Instead of installing conventional heating, a basic structure was built using common materials: a steel container, sand, and a network of pipes. No advanced electronics, no complicated systems, just physics applied in a smart way. At its core, this system is not about generating heat, it's about storing it. That distinction is important. Most modern heating systems focus on producing heat when needed, which requires constant energy input. This method flips that idea completely. It captures heat when it is available and holds on to it for later use. The science behind this is surprisingly straightforward. Every material has the ability to absorb and retain heat, a property known as specific heat capacity. Some materials do this better than others. Water is commonly used because it can store a lot of heat, but it comes with limitations like boiling, evaporation, and corrosion. Sand, especially dry and fine-grained sand, offers a different advantage. It can be heated to very high temperatures without breaking down, and once heated, it releases that energy slowly over time. When sand is packed tightly inside a container and heated, it essentially becomes a thermal reservoir. The larger the volume and the higher the temperature, the more energy it can store. This is where the idea scales from something simple to something powerful. Even a relatively small setup can hold enough heat to make a meaningful difference in daily heating needs. What makes this approach especially interesting is how accessible it is. The materials required are not rare or specialized. Steel containers, pipes, insulation, and dry sand are all widely available. This means the barrier to entry is not about access, it's about understanding and execution. Before getting into construction, it's important to clear up a common misunderstanding. This is often called a sand battery, but it does not store electricity. There are no chemical reactions taking place like in traditional batteries. Instead, it stores thermal energy, pure heat. That means it doesn't power appliances or lights directly. Its role is focused, storing heat and releasing it when needed. This concept is not entirely new. In fact, it shares similarities with older heating methods that have been used for centuries. Systems like masonry heaters work on a nearly identical principle. They generate a large amount of heat in a short period and store it in a dense material, which then radiates warmth slowly over time. The difference here is scale and flexibility. Instead of being built into a wall or structure, this system is standalone and can be adapted to different setups. There's also a practical side to consider. This is not designed for every living situation. It requires space, some level of construction skill, and the willingness to work with tools and materials. For someone living in a city apartment, this isn't realistic. But for those with land, workshops, or off-grid setups, it becomes a highly practical option. Another key point is energy input. While the system itself doesn't require electricity to store heat, it still needs a source to charge it. That heat can come from various places: solar, thermal systems, wood-burning setups, or even excess electricity converted into heat. Once the sand is heated, however, it holds that energy without needing continuous input. The efficiency of this system depends heavily on insulation. Without proper insulation, stored heat will escape quickly, reducing effectiveness. With good insulation, the heat can be retained for days or even weeks. This is where careful construction and material choice make a significant difference. There's also a broader implication to this approach. It challenges the idea that modern problems always require high-tech solutions. Sometimes, the answer lies in understanding basic principles and applying them in a practical way. Instead of relying on complex systems that require maintenance, fuel, and constant input, this method focuses on simplicity and durability. As more people explore off-grid living and self-sufficiency, systems like this are gaining attention, not because they are trendy, but because they solve a real problem in a reliable way. Heating is one of the biggest energy demands in cold, climates, and reducing that dependency can have a major impact. What makes this especially powerful is the control it gives back to the individual. Instead of being tied to external systems or rising energy costs, you create your own heat storage. You decide when to charge it and how to use it. That level of independence is rare in modern infrastructure. This is not a miracle solution. It won't fix poor insulation or inefficient buildings. In fact, it works best when paired with a well-sealed, energy-efficient structure. The better your building retains heat, the more effective this system becomes. It's a partnership between storage and conservation. As we move into the next phase, the focus will shift from understanding to execution. Every step from selecting materials to building the core system will be broken down clearly. Because once you understand how this works, the next logical step is simple. Build it yourself. Turn simple materials into a silent heat system that works for days without fuel or electricity. Now the shift happens from idea to execution, because understanding the concept is only half the story. The real advantage comes when you build a system that actually works in your environment and delivers consistent heat without depending on external energy sources. The goal here is not complexity. The goal is reliability, simplicity, and long-term performance. Everything starts with a container, because this is the core structure that holds your thermal mass. A steel drum or vertical tank is ideal, because it can handle high temperatures without degrading the size you choose. Directly impacts how much heat you can store. A small 55-gallon drum can work for testing or supplemental heating, but if you want meaningful results for a home, you need to think bigger. Something in the range of 250 to 500 gallons creates a system that can actually carry heat across multiple days. Once the structure is selected, the next step is preparing the internal heat exchange system. This is where most of the performance is determined because the pipes inside the sand control how efficiently heat moves in and out of the system. A continuous steel pipe formed into a coil works best because it maximizes surface area. More surface contact with the sand means faster charging and more efficient heat extraction when needed. The coil should run vertically through the container, starting from the bottom and exiting at the top. This natural flow supports better heat distribution as hot air rises inside the system and cooler areas settle below. Keeping the energy movement balanced inside the sandmass spacing is important. The coil should not touch the walls of the tank because direct contact creates uneven heating and reduces efficiency. The goal is full immersion in sand with minimal air gaps. Before anything is sealed, the system must be tested, because once the sand is added, any leak becomes a serious problem. Pressurizing the pipe and checking every joint ensures that the system is airtight and ready for long-term use. Skipping this step is one of the most common mistakes, and it turns a simple build into a costly repair later. Now comes one of the most critical stages, filling the tank with sand. This sounds simple, but it determines how well the system performs over time. The sand must be completely dry. Any moisture trapped inside will turn into steam at high temperatures and create pressure inside the tank, which can damage the structure or reduce efficiency. Dry fine silica sand is preferred because it handles heat better and packs more tightly than regular construction sand. The filling process should be slow and controlled. Adding sand in layers and compacting each layer removes air pockets, which are the enemy of heat transfer. Air acts as insulation in the wrong way. It blocks heat from moving through the sand. So the tighter and more uniform the fill, the better the system performs. When fully loaded, the sand should sit just below the top, leaving a small expansion gap to handle temperature changes. Once filled, the container must be sealed securely using a high-temperature resistant cap and sealant. This prevents heat loss and protects the internal structure from external moisture or contaminants. From this point forward, insulation becomes the defining factor between a system that works for hours and one that works for days. The outer insulation layer should use materials designed for extreme heat. Ceramic fiber is one of the best options because it can handle very high temperatures while minimizing heat loss. Wrapping the entire tank, including the base, ensures that energy stays inside the system instead of leaking into the surrounding environment. The bottom is especially important because heat naturally transfers into the ground if not properly insulated. After insulation, a protective outer layer is added using sheet metal. This is not for heat retention but for durability. It shields the insulation from damage, weather, and pests, turning the entire unit into a long-lasting structure. that can operate in outdoor conditions without constant maintenance. Placement of the system is just as important as how it is built. Installing it inside the main living space without proper protection is not safe. The best approach is to place it in a separate structure, like a small shed or utility building, near the house. This allows safe operation while keeping a pipe runs short enough to minimize heat loss during transfer underground. Insulated piping can then connect the system to the home. Connecting the system to your existing heating setup depends on what you already use. Radiant floor systems are the most efficient because they operate at lower temperatures and distribute heat evenly throughout the space. Baseboard systems can also work using a heat exchanger to transfer energy without mixing fluids. Forced air systems require an additional step by passing air over a heated coil, but they still benefit from the stored heat. To control the system, a temperature-activated switch ensures that heat is only distributed when the stored energy reaches a useful level. This prevents the system from circulating low-temperature fluid, which would reduce overall efficiency and comfort. This small control element makes a big difference in real-world performance. Charging the system is where flexibility comes in because the heat source can vary. Depending on what is available, solar thermal collectors can capture heat during the day and transfer it into the sand, creating a reserve that lasts into the night and beyond. Wood-based systems like rocket heaters can rapidly inject large amounts of heat in a short time, storing it for gradual release. Excess electricity from solar panels can also be converted directly into heat using resistive elements, making use of energy that would otherwise go unused. In practice, the system does not need constant charging. Maintaining a consistent temperature inside the sand is enough to ensure reliable output depending on insulation and usage patterns. Charging every few days can keep the system operating continuously through cold periods. Performance depends heavily on the building itself, because no heating system can overcome poor insulation. A well-sealed home multiplies the effectiveness of stored heat, reducing daily energy demand and extending how long each charge lasts. This is where the real efficiency appears, not just in the system, but in the combination of storage and conservation. Maintenance is minimal compared to traditional systems because there are no burners, no fuel lines, and no complex electronics. The primary focus is checking the integrity of the pipe system before each heating season, ensuring there are no leaks, and that pressure remains stable over time. Once confirmed, the system can operate with very little intervention. What this creates is a different kind of heating approach, one that shifts from constant consumption to controlled storage. Instead of paying for energy every day, you capture it, store it, and use it when needed. It removes dependency on external systems and replaces it with something predictable and self-managed. And that is where the real value shows up, not just in cost savings but in resilience. Because when the grid fails or fuel prices rise, the system keeps working quietly in the background, holding and releasing heat exactly when it is needed. Without noise, without moving parts, and without ongoing expense,